Sticks. All right, but we're going to talk about spins today, not about sticks. So I want to continue our discussion of the concepts and theory behind NMR spectroscopy. And again, this is not going to be about math or anything to that extent, but we're going to be thinking very, very qualitatively. All right, so when we last left things, we had said that there are two spin states for a dipolar nucleus like a proton or C13. There's spin up and spin down. And if you have an applied magnetic field, there's a small energy difference between the spin up state, what we're calling the alpha state, and the spin down state, what we're calling the beta state. And because that energy difference is so small, unlike IR spectroscopy or electronic spectroscopy, UV vis spectroscopy, where the energy differences are very big and all of your molecules are in the ground state, here there's only a minuscule number of nuclei in the lower state more than the number in the upper state. We said if we take 2 million protons, out of those 2 million protons, depending on the applied magnetic field, it will be 50 or 80 or thereabouts difference in population. And it turns out that difference in population is going to be extremely important because it is only that differential population that's going to be able to get us a signal. All right, so if we think about things in an XYZ coordinate frame, and I'll talk more about an NMR spectrometer in a second and how it works. But imagine for a moment we have some coordinates. So the x coordinate is coming out of the plane, the y coordinate is in the plane, and the z coordinate is pointing up. And we're going to have our applied magnetic field B naught pointing upwards. That kind of makes sense. These superconducting magnets are always vertical because you've got this big pot of liquid helium surrounded by a vacuum vessel, surrounded by liquid nitrogen, surrounded by a vacuum vessel. And those small amounts of population, that small differential of population with spin up is going to give rise to a net magnetization. Now, in other words, a way to think about this is, for most of our cases, we're going to have one nucleus pointing up, one nucleus pointing down in their spin, and there's no net vector here. Those vectors cancel each other out. But for that small differential of excess vectors, you're going to have some net magnetization along the z-axis. Now, the way it works when you apply a magnetic field is you actually have those vectors they're processing around. So in other words, they are processing at that resonant frequency, at the Lamar frequency, at 500 megahertz for 117,500 Gauss magnet. So we actually can represent this by saying, OK, we've got spins sort of pointing in every which way, and I'll just draw two directions. They're all processing around. So remember, this is only the differential population that we're worried about, because already for every one where you have one up and you have an opposing one spin down, those vectors are going to cancel each other out. Now, the other thing is they're not quite on axis. In other words, they're not like this. It's like a gyroscope if you've ever hung it from a string. The gyroscope doesn't, who's hung a gyroscope from a string as a kid? The gyro in physics lab or something. The gyroscope doesn't hang vertically. It kind of hangs off axis and goes around like this. But if you think about it, since those spins are not bunched up, for every one that's processing like this, there's another one that's opposite it. So in other words, if it were just like this, you'd say, oh, there's a net magnetization along the z-axis, but also a net magnetization along the y-axis. But there are other spins that are like this, and they're all going around. So everything's canceling out except the net magnetization along the z-axis. All right, what I want you to imagine right now is that we're going to place a coil along the x-axis. And we're going to put energy into that coil. We're going to apply a magnetic force. And I want you to think classically, because the quantum mechanical thing is going to be we'll flip the spins. I'll show you that in a second. But you have your net magnetization along the z-axis. And think back to classical physics. If I apply a force along the x-axis, right-hand rule and all of that good stuff, we rotate our vector downward. So after we apply a pulse, I'll just say a pulse, if here's our net magnetization, when we apply an RF pulse, our net magnetization moves along the y-axis. And so I guess if I want to, actually if I want to represent it, I'll just say x, y, z, and I'll say here's our net magnetization. And as you'll see in a moment, we're going to have continued precession. And again, if you're worried about the fact that all of our vectors are not lining up, that they're all precessing like this, just think, as I apply a pulse and drive my magnetization from the z-axis onto the y-axis, the vector sum is right along the y-axis. Even though there are some that are like this, I drive it down, they're countering each other. There are some like this, and drive it down, they're countering each other. And so our net magnetization ends up along the y-axis. Does that make sense? All right, let's come back to our spins to see what this means. So the way I was trying last time to represent this very small difference between the alpha state and the beta state was to show some spins pointing up in the alpha state and some spins pointing down in the beta state, and to try to represent this minuscule difference in population, what I did for the purpose of my drawing was I drew 6 with spin up in the alpha state and 4 with spin down in the beta state.
Individual nuclei, right?
Those are representing exactly the spins of individual nuclei. So in other words, if we had a mole of, or more realistically, if we had a millimole of CHCl3, proteochloroform, in our NMR tube, what this would represent would be the nuclei of the hydrogen there, and we would have, out of that millimole of nuclei, we would have a small excess in the alpha state, and they would all be precessing. All right, so if we apply an RF pulse, and now I'm going to be a little bit specific, if we apply a pulse long enough that is what's called a 90-degree RF pulse, or a pi over 2, that's just radians and degrees, your choice, and they get used interchangeably. What that does is it equalizes the population of alpha and beta state. And so I'll represent that by 5 spin up and 5 spin down. And this situation is exactly the situation that we have at the end of my little drawing over on the left-hand blackboard. In other words, here's our net magnetization. And so the key is now we have no net magnetization spin up, no net magnetization spin down. But the very important point is we have the net magnetization focused along the y-axis. It is not diffuse, it is not pointing in all directions, we actually have net magnetization in the xy plane. And if we apply a longer pulse, a more powerful RF pulse, so again, I will represent our 6 little arrows and 4 little arrows representing our differential populations of the beta state. If we apply a more powerful RF pulse, what we call a pi RF pulse or a 180-degree RF pulse, I can invert the population. In other words, I will represent that by 4 arrows pointing up and 6 arrows pointing down. And if I want to draw that on my diagram, can anyone tell me what I do with my net magnetization on my little XYZ diagram at this point? It's going to point down, exactly. All right, and this is the damning thing, well, one of the many damning things about NMR spectroscopy is no matter what you do with your pulses, you are limited to the difference in population that occurs between the alpha and beta state. And later, when we start to talk about 2D NMR spectroscopy, we're going to learn about one of the common techniques now, which is to go ahead and have polarization transfer. Now, think about what I said before in the equation relating the Boltzmann distribution to the energy difference. And remember how the magnetogyric ratio for carbon was 1/4 the magnetogyric ratio for protons. That means that roughly the Boltzmann distribution is going to be a quarter as big on differential population for carbon as it is for protons. So when we get into techniques like HMQC, which is a 2-dimensional technique, one of the tricks of this technique is to transfer the larger but still minuscule population difference from proton to that of carbon. But again, what's damning is you never can get away from the fact that out of 2 million protons at 500 megahertz, there's no way to exceed that. I think I said 81 out of 2 million population difference, with the exception of some very specialized techniques that involve, for example, unpaired electrons and free radicals, or xenon atoms for that matter, and special optical techniques. All right, so we have our differential population, and we know that if we apply a pulse of the right length, we can drive that population to have a net magnetization in the XY plane. Now let's take a look at how we get a signal out of the spectrometer. All right, and again, we have a coil, and I'm going to represent that coil as being along the x-axis. That's a little bit of an oversimplification. And now we have our net magnetization in the xy plane. And as I said, it precesses. And so I'm trying, of course, it's hard in 3 dimensions. I'm trying to represent this as precession in the xy plane. I'm trying to represent that with a curvy little arrow. But what I'm really saying is you have your net magnetization, and it's moving around. Those vectors are moving around. And we'll just take a single nucleus like chloroform. It's precessing at the frequency, we'll call it V, call it nu. So like at 500 megahertz. Sometimes it's called the Lamour frequency. So for example, at 500 megahertz for a 117,100 500 Gauss magnet. And NMR spectroscopy was actually discovered by the physicists and then rejected by the physicists because they figured that there would be this universal property of a proton of how fast it precessed in any given magnet. And when we come next time to the concept of chemical shift, we'll see that the frequency, the magnetic field that the proton feels is modulated by the nature of the molecule, by the environment in the molecule. Hence, different types of protons precess at different frequencies. Chloroform precesses at a different frequency than TMS. The CH2 groups of ethyl alcohol precess at a slightly different frequency than the CH3 groups. These differences in frequency are very, very small, but they were upsetting to physicists because physicists figured this has to be a universal property of protons, and when they saw it varied by magnetic environment in the molecule, they gave it the contemptuous term chemical shift. Anyway, so what happens if you have a coil and you have a magnet rotating in that coil? Think back to your physics. Well, eventually we'll get to relaxation, but right now let's just imagine.
It's creating a negative X direction. Magnetization there. I think I'm thinking about this wrong.
Anyone ever done this again as a kid, where you take a magnet and you spin it in a coil?
Oh yeah, it creates an electric thingy.
An electric thingamajiggy, a current. Yeah. Yeah, we get a current in the coil. And this is the basis for all of this stuff. So while the nuclear generators are working hard in San Onofre making steam, what they're basically doing is turning a magnet inside a coil. In practice, it's done with armatures and wires, but it is the exact reverse of a motor. And the simplest motor you can make involves taking a coil and taking a magnet on an axle and putting an alternating current in it. And the reverse, when you spin a magnet inside a coil, you get an alternating current. And so the current looks something like this. On the x-axis, I'm going to plot voltage. And on the y-axis, I'm going to plot time. And an AC current is simply the voltage oscillates in a sinusoidal fashion. So we get this cosine wave, and it goes on. You can call it a sine wave if you want. And technically, I guess I should be at the peak of my wave right here. But what that's saying is as the vector is like this in relation to the coil, your voltage comes to a peak, and then as it gets along the negative x-axis, you come down and it gets to the negative y-axis and it comes up. And for your 117,500 Gauss magnet, we're going ahead and having this frequency be 500 million cycles per second.
The oscillation of the nuclei has to be in the XY plane.
It has to be in the XY plane.
How is that controlled by the?
That comes from the pulse that we apply. So remember, we have our net magnetization along the z-axis. We apply a pulse. That pulse drives the magnetization into the xy plane along the y-axis, and we get precession. That pulse is equalizing the population of alpha and beta states, and in doing that is basically making same number spin up, same number spin down, but it's directing them together in one way. And in practice, when you apply pulses, they actually come in fours. So for those of you who've run a spectrometer, how many of you have run an NMR spectrometer? And you do number of scans is equal to 4 or 8 or 16, that's no accident, because we are actually doing what's called phase cycling, which means in order to cancel out artifacts, we do a set of 4 experiments or 8 experiments. So you first do a positive X pulse, for example, then you do a negative X pulse, then a positive Y pulse, then a negative Y pulse. And then we average them all together, and that reduces artifacts. So the big problem with all of this is we're dealing with really minuscule signal. And so the killer in NMR spectroscopy, we've got very few nuclei that are available. We've got very small magnetic vectors. We get very small signals. And the whole key is how to get enough signal out of there over all the noise that's coming so that you don't need an entire NMR tube full of pure sample, and you can take just a few milligrams or less of compound in your NMR tube. So if I want to give my very, very simple diagram of an NMR spectrometer, so you have a solenoid. A solenoid is just a coil in which you have electricity. It's a superconducting coil. Superconducting so that you have the electricity flow forever and you don't have to keep putting more electricity in it. To do this, you have it cooled in liquid helium. In order to minimize the evaporation of the liquid helium, you have a vacuum around it. That's a Dewar vessel. Any of you who has a vacuum thermos for your coffee has that. But in order to further minimize the loss, you have that Dewar contained in liquid nitrogen and a second Dewar around there because liquid helium is expensive and you don't want to replace it that often. So you have your solenoid, and then you have your NMR sample. In an NMR tube. And then you can think of it as your coil. God, this is a horrible drawing. So your coil goes to an amplifier. So this is just like a radio at this point. Your coil goes to an amplifier because you're getting a minuscule signal. Who's ever opened an AM or FM radio and looked inside of it? So the first thing you see is some sort of metal coil, right, on an armature. That coil, one of them is tuned for the AM frequencies, and there's a different one tuned for the FM frequencies. Or if you have a stereo and you have one coil that's your FM antenna and one coil that's your AM antenna. Obviously, none of this is internet radio. So anyway, you have two different coils. That comes back to what I was saying before about having, remember I mentioned broadband detection and the proton coil? So in general, different coil shapes work well for different frequencies. And so one coil's on the inside. And so if we are doing proton NMR, it's best to have your proton coil on the inside. If you're trying to get the best carbon NMR, in general, it's best to have a coil tuned to carbon's frequency. Remember, they differ by a factor of 4 on the inside. Okay, so then for modern NMR, what you do is you go from an amplifier, we're going to go digital. So after you get a signal, the signal is analog. After you go to the signal, in order to process it, we're going to digitize it. That simply means convert it to bits and bytes. So in other words, instead of having a voltage here that's, 1.007823 millivolts, you're basically going to convert your voltage to binary and say that's 1110011, etc. So we go to an ADC, or analog to digital converter, and then that goes to a computer and to a printer. And for those of you who've run an NMR spectrometer, you probably know the command RG, receiver gain. Who's heard that one? What you're doing there is basically saying, OK, we want to fill up have as big a number. If we had an 8-bit analog to digital converter, in other words, 8 digits of 0 or 1, you want your biggest signal to fill up that thing to be as close as possible to 1, 1, 1, 1, 1, 1, 1, whatever 8 ones is. But if it's bigger, you're going to saturate it, and then you're going to get all sorts of artifacts and clipping. But if it's too small, if you're representing your maximum signal by 0, 0, 0, 0, 0, 1, 1, 1, then by the time you're down to very small signals, you just don't have the digital capacity for them. So that's what you're doing when you're adjusting the receiver gain. OK, so that's my pigeon diagram of an NMR spectrometer and what's happening. And as I've said, it's more complicated because we have coils in all 4 directions, and you're going positive X, negative X, and so forth. All right, the big advance, which of course is accepted as ubiquitous in NMR, is the Fourier transform. And I can guarantee all of you are going to be able to intuit what this is with zero mathematics. I have nothing against math, but there's an incredible power to being able to actually understand stuff rather than calculate it. Extras needed back here? All right. I'll give you the simplified version, and then I'll explain a few details. But let's start with the simple version. All right. So this is a cosine wave corresponding to a precession at 1 cycle per second. In other words, every second we go around once. If we take this function and Fourier transform it, we end up having an amplitude axis and a time axis. And what the Fourier transform does is converts the time axis to a frequency axis. So we still have amplitude. And now we've gone from time to frequency. And so if I write a little graph, 0, 1, 2, 3, I can represent, God, that's lousy and uneven. I can represent the Fourier transform as a peak at 1 hertz, 1 cycle per second. And to a first-order approximation, that's all there is to a Fourier transform. It is taking that oscillation and saying, what's the frequency of the oscillation? So if I take this second graph here, and we Fourier transform that, what's the Fourier transform of that second graph? A peak at 2 hertz. Now, if you've ever looked at your free induction decay. We'll come to what a FID, but you've collected an NMR spectrum. You see that wiggly thing. That wiggly thing is the free induction decay. That's what's going into your coil at each cycle. If you've ever looked at it, it's not a simple sine wave. It is a simple sine wave if you only have one type of proton. So if you do it on pure CdCl3 that has a little CHCl3 and not a lot of water, not a lot of TMS, you'll just see a sine wave that decays, and I'll tell you about that in a second. But normally what you see is something that has more complication to it. And so here what I did, literally, this was just done in Excel as an example, is I took our 1 cycle per second graph, and I took our 2 cycle per second graph, and I added them together to get this red curve. And so if we take the Fourier transform of this red curve, again we get frequency. I'll just represent that as 0, 1, 2, 3, etc. But now the Fourier transform is going to be a peak at 2 hertz, or peak at 2, and a peak at 1. In other words, basically what that's saying is this is just the superposition of a 1 cycle per second current and a 2 cycle per second current. And obviously in an NMR spectrum in which your ethanol may have 4 peaks for the CH2 group and 3 peaks for the CH3 group, it's going to be a heck of a lot more complicated than that. Parts per million is like cycles per second. And more specifically, if you have 500 megahertz per session, then you're going to have 500 hertz is 1 ppm, 1,000 hertz is 2 ppm, 1,500 hertz is 3 ppm. And if you have 300 megahertz per session, if you have that 70,000 Gauss magnet I talked about last time, you're going to have 300 hertz is 1 ppm, 600 hertz is 2 ppm, 900 hertz is 3 ppm. All right. Now, I'm not exactly playing honest with you. Because if you have a frequency at a certain, so remember, this is amplitude and time, and the Fourier transform transforms the time axis to a frequency axis. If this goes on forever, then you end up with a line of infinite sharpness. What actually gives rise to the sort of peaks you see is something at this frequency but that dies off with an exponential decay. And so when you Fourier transform a cosine wave dying off with an exponential decay, you actually get something that looks like an NMR peak. And I'm not a great artist, but I will try my best to represent the shape of this peak, you have little wings coming out, and this is what you call a Lorentzian line shape. A Lorentzian is just a mathematical function that corresponds, it's y equals 1 over x squared plus 1. And you'll later on see I have a simulation program that actually incorporates this that you'll get to play with. However, the main point is peaks are not infinitely sharp, and this doesn't go on forever. The reason this doesn't go on forever is what's called relaxation. So there are two types of relaxation. There's longitudinal relaxation, sometimes called spin lattice. Sometimes you'll also see it referred to as T1 relaxation. And what this involves is re-equilibration of the alpha and beta states. By transfer of energy to thermal motions in the sample. Now, an easy way to think about this is when we applied our pulse, we drove our magnetization down into the xy plane. In other words, what that means is we took the alpha and beta states that were at a Boltzmann distribution, the natural distribution to be in a magnet, and we forced them to an unnatural distribution. But eventually, due to spin lattice relaxation, your nuclei flip their spin back to the z-axis, or the population returns. And now you see why you have an exponential decay. It's a half-life process. Any given nucleus has a finite probability of having its spin flip back to the natural population states. And so that's like radioactive decay. That occurs with a half-life. Called the relaxation time, or more specifically, the T1 relaxation time. So that gives rise to our exponential decay. That gives rise to our exponential fall off. Now, there's a second type. T1 relaxation is a little more important in small molecule NMR spectroscopy, but there's a second type of relaxation that's also important, transverse relaxation, sometimes called spin relaxation, sometimes called T2 relaxation. And what transverse relaxation does is involves interaction of spins with other spins in the sample, leading to an unbunching of spins in the xy plane.
where does it lead to?
Unbunching of spins in the xy plane. So interaction with spins of other nuclei leads to unbunching of spins in the xy plane. What does that mean? Well, remember I said when we applied our pi pulse, all of our net magnetization was along the xy plane, and all the spins of the same type are precessing together. But if they unbunch, if due to getting tickled by other nuclei, some precess a little faster and some precess a little slower. I'm talking now for one type of nuclei, like the hydrogen and chloroform. What happens to the net magnetization from that vector? So look at the vectors are starting to cancel each other out. We're still in the xy plane. In other words, our population of alpha and beta states hasn't been perturbed. We still have that non-Boltzmann population from the initial pulse, where it's, in this case for a pi pulse, 50% up, 50% down. But now we're losing our focus in the xy plane. As they unbunch, our magnetization gets smaller and smaller, and our signal falls off. And so through these relaxation processes, through T1 relaxation and through T2 relaxation, we have a fall off in our peak, in our intensity. And so we get a line that has a width to it. All right. There are two concepts that are closely related. One concept we saw is the whole idea of the Fourier transform gives rise to a peak with a width to it. But the other thing is that line width is related to the uncertainty principle. So we can always go ahead and blame quantum mechanics. The gist of the uncertainty principle, as you've probably heard it, is that you cannot know with exact accuracy both the position and the velocity of an object. To put it in other terms, the longer you can make a measurement, the more accurately you can know the velocity. Or the longer you make a measurement, the more accurately you can know the angular velocity. That's the same idea as an infinitely sharp line. If I have something precessing and we can watch it forever, we can know that this is precessing at 500.0003215 cycles per second. However, if you only get to look at it for a little bit, you say, well, it was moving fast. It wasn't moving at 100 cycles per second. It wasn't moving at 1,000 cycles per second. It was somewhere around 500 cycles per second. And expressed mathematically, what we get is that delta nu times tau is equal to 1 over root 2 pi. What this is the, I'll call this the half line width, and you'll see why in a second. And this is, tau is the half-life of the spin. And so let's come back to our Lorentzian line shape. And let's come to some hypothetical ideal. So remember, we're talking frequency here. All right, so our hypothetical ideal is, this is the hypothetical exact frequency. But the point is, if we can't measure the frequency exactly because we're not measuring it for infinitely long, because the frequency is, the line is relaxing, we can only tell, well, it's somewhere around here. So you get a peak that has some width to it. And this is our delta nu. And from your point of view, what you often think of and what I think of when I look is this is what I like to call the line width. In other words, it's sort of at half height. In other words, it's 2 delta nu. Because here we're saying, well, it's within plus or minus delta nu of this center value, but we can't tell exactly. Here I look and I say, OK, this line is this fat. All right, so what does that mean? If we have a tau equals 2 seconds, that leads to delta nu is equal to 1 over root 2 pi is equal to 0.11 hertz. That's 0.22 hertz line width. If I have tau, and this is of course seconds, if I have tau equals 1 sec, then delta nu is equal to 1 over, well, I'll just skip the equation here. It's equal to 0.22 hertz is equal, and that's 0.44 hertz line width. Now, the relaxation of protons typically occurs on the order of 1 or 2 seconds. So there is a real theoretical limit to how sharp your peaks can be, because that theoretical limit is going to be determined by their relaxation. Carbons are funny because they relax more slowly. And there, the reason that you end up not having big peaks for quarks, you know that your quarks are always quaternary carbons, your carbonyls and carbons with 4 things connected, are always very short, is because between pulses, you don't go ahead and have full return of magnetization.
How can you vary the half-life of the spin? Like, you change the temperature?
No, you don't have control of it. I mean, you have a little bit of control. If you remove paramagnetic, if you add paramagnetic impurities, then, which we actually do in experiments like the inadequate experiment, then you can decrease the half-life. If you remove paramagnetic impurities, for example, if you, by freeze pump thaw degassing, remove dissolved oxygen, which is paramagnetic from your sample, you can decrease the T1 relaxation, because remember, it's the interaction with nuclei that flips the spin, and so you have oxygen that's paramagnetic. All right, so the point is exponential decay leads to line broadening, and if you have a little bit of exponential decay, like so, then you get a sharp line. If you have a lot of exponential decay, you get a broader line. So these are both on Fourier Transform. Yeah?
Can you reduce the effect of the other species by aligning those nuclei as well?
You can do various tricks. So in the case of molecules that have very restricted motions, like solids, T2 relaxation becomes critical. And in the case of solids, to get good spectra, you have to spin the sample at what's called the magic angle to reduce relaxation, T2 relaxation. So there are little tricks. But for the most part, relaxation isn't a problem. Proton NMR, it's a good thing because it allows you to repeat your experiments. And that brings us to the next, and I think perhaps the last thing that I will talk about. And as I said, carbon NMR can be a pain because the relaxation is so slow that it makes your peak small. All right, so the last thing I'll talk about is signal averaging. Now, I've already hinted that you have this notion of phase cycling, that you really have to do experiments in sets of 4 or 8, with the exception of certain pulse field gradient experiments that I'll talk about later that reduces phase cycling. This becomes important in 2D NMR. But you go to all the trouble to synthesize a compound, make up an NMR sample, you collect the spectrum. It's no big deal to collect data for a minute instead of for 5 seconds, so that's not a big deal. But the big problem that we have, as I said, NMR is a very insensitive technique. You have a very low signal. You're not fighting the low signal. What you're fighting is the noise. And when we talked about the cryoprobe the other day doesn't increase the amount of signal, but it does decrease the amount of noise, electronic noise. Think of noise as static. You tune to an FM radio station that's far away, you hear a lot of static. Doesn't occur on internet radio because it's all digital. But you tune to a station that's far away, there's a lot of static. So what can you do? The static is random. So if you go ahead and collect repeated signal, you can average it out. The signal to noise varies as the square root of the number of scans. In other words, if I collect more data, I get more signal to noise, but the noise is going up as well. It's just going up randomly. So in other words, if I go from 16 scans, which is a very reasonable number, to 64 scans, I don't quadruple my signal to noise, I double the signal to noise. And so if you're collecting a C13 NMR spectrum and you've got a lot of noise, you say, oh, well, if I go ahead and I want to make my spectrum twice as good, I've got to collect data 4 times as long. If it's midnight and you've been collecting since 10 p.m., know that your spectrum's only going to get a little bit better, only 1.4 times better if you wait till 2 in the morning. If you wait till 6 in the morning, it's going to get twice as good. If I double the concentration, I'll also double the signal to noise. So I'll say 2x. So again, I'm sitting there at midnight and thinking, my God, I don't want to be sitting here till 6 a.m. I run up to the laboratory, I dump some more sample in my NMR tube, and now by 2 in the morning, I have twice as good a spectrum. So that's the general gist. There are a number of other aspects. I think I give us a reading in Claridge that I'd like you to look over. There are a number of other aspects of Fourier NMR spectroscopy, including digital resolution. But suffice it to say right now, we collect data for a few seconds. The data is becoming, as your signal's falling off, like so. We have more noise here relative to signal. So we don't want to collect data forever. So in the end, we strike a compromise. We collect for a few seconds. We average the data. We perform a few mathematical operations to smooth it out because the Fourier transform of a truncated signal, if I just truncate my signal, the Fourier transform actually looks more like this, where we have a couple of wiggly things around the peak. So we apply weighting functions. That's called the exponential multiplication. We apply weighting functions so you don't just truncate, you actually drive the signal down so that you get a better line shape. And you can read a little bit more about that in Claridge. All right, we'll pick up next time talking about chemical shift, and at that point we'll start to talk about differences between different types of protons within a molecule.